podcast, and my guest today is Ashley Bray, sales engineer at Volume Graphics. We're going to be talking about the uses of CT scanning in industrial applications. Welcome to the show, Ashley.
Thanks very much for having me, Brian.
Great. I guess to start out, could you tell me how is industrial CT scanning being used for applications like quality control or analysis?
That's a pretty big question, I guess. And in the early days, it started out in just kind of simple failure analysis when CT in industry was seen as something slow and expensive. And since then, it's branched out into all sorts of applications. And not only different industries and applications, but even if we break it down to, let's say, per industry, per company, the beauty of CT is that there's an opportunity for it to be put in somewhere within the company throughout the entire product life cycle. So from R&D, where you might be materials testing, to rapid prototyping, where you might need to check how that's being created, measured, down to first article inspection, or you can even have inline systems that then measure the actual process itself. So nowadays there's CT everywhere, and it's no longer just failure analysis. It's not just measurement and metrology. There are so many applications that, fortunately, it's what keeps me excited about the job itself is the plethora of customers and industries that we get to speak to.
Well, what are some of the advantages of the CT scanning technology compared to other approaches that people have typically used for these applications?
You could probably break that down into kind of two separate things. So one is, like I'd mentioned, the number of applications, but the reason there's so many is the things that CT has to offer over different types of analyses. So obviously the first huge advantage is being able to see inside whatever it is that you're looking to measure. So if there's really complex geometries, for instance, certainly with things like additive manufacturing, you can now create these super complex geometries that once they're created, you have no idea what's inside. And the only way historically to do it would be to cut it open, which obviously a lot of the time defeats the object of you actually trying to measure the part in the first place. So being able to see inside, the fact it's non-destructive. And another huge one is that when we scan it, we have the option to scan the entire part. So if we now were to compare this with, let's say, traditional measurement methods like CMMs or laser scanners, then there's a huge amount of operator influence, because depending on how they lay this sample on the table will affect how it's measured. And then they can't digitize it all in one go. You'd have to flip it over at some point. The beauty of CT is you digitize the whole thing, and it doesn't even matter how it's really laid inside the system. So anybody who comes along and puts a part inside the CT system, it doesn't matter how it's orientated, you've now got the whole part digitized. So the beauty of that is obviously the extra options that you have in terms of measuring from one side to another. Again, having a look at inside things like this. So in terms of applications, this is what opens up many doors. And then processes. So I'd mentioned the operator, how they lay it inside. So obviously one of the major things is there's no operator influence on these measurements anymore in that respect. And if that's the case, then it's scalable. So now if you have some sort of analysis you want to carry out across multiple sites, it doesn't matter anymore who the operator that uses it. It doesn't even matter really that much what your CT hardware is. The results will come out roughly the same, and that means as soon as we at Volume Graphics get it and start doing our analyses, you'll get something repeatable, whether it's in Asia, the US, or in Europe, can all work to the same template.
Well, physical scanning then is just part of this process. What kind of role does software play in turning the images you get from the scans into something that's usable for these applications?
Now, I obviously don't want to minimize the effort that the hardware guys put in to create CT scanners, because they're wonders of modern physics and technology. But what they create is a digital model, and then that's it. So until you get software involved, there's nothing you can do with it. Maybe have a look at a pretty 3D representation if you're lucky. But the real useful information that you get is nobody buys a CT scanner just to have a 3D model. They buy it to carry out analyses. And that's where then the software becomes so important, because all the analysis is now done in the digital realm. And so the software itself and the analyses are done is essentially what gives the customer the data that they actually need, whether that be dimensioning data or whether that be data that refers to things like fiber orientations in plastics or so many different things. But the point is, until you get the software involved to start doing focused and detailed analyses, then there's nothing quantifiable that comes out.
Are there types of structures or types of materials where this type of scanning is not going to be a good fit for certain types of end users?
Yes, there are limits to what you can scan, but I guess an analogy is a little bit like buying a car. So some cars need to go off road, some need to go around tracks, some just want to go as fast as possible in a straight line. So you can kind of extrapolate that out and say that CT systems can be similar. They'll focus on certain areas. So there are limits, but it's not just really about the material. It's about what you want to analyze in whatever your part is. So you can scan something as large as an engine block, for instance. There are scanners that will do that. And so one of the common applications if you're scanning engine blocks will be to look for porosity within these castings. Now, if you're looking for pores that are maybe a millimeter, for instance, in size, then that's absolutely not an issue. You will definitely be able to see those. If you're looking for something like 10 microns, then you're asking an off-roader to keep up with a Ferrari. So there are limits, but it depends on what the application is and not just on the type of material. But I guess one thing you could go by is the denser the material gets, the more challenging it is for a CT system. But I certainly want to make sure that I don't give the impression that denser materials can't be scanned. That's not the case.
Now, to use CT scanning, obviously there has to be a scanner there, and you've got to have someone to operate it. Are companies typically investing in their own scanners, or are they utilizing third-party providers? And is that changing?
It's a bit of both. It did used to be the case that they almost exclusively invested in their own scanners because they were quite expensive and there weren't really many third-party providers that offered those sorts of services. But now that CT has become relatively normal in industry nowadays, that also means there's plenty of service providers that will take samples from customers and scan them on their behalf. So I wouldn't necessarily say it's going more in that direction, but there's certainly many more options out there if you're not ready to purchase a CT system yet yourself. And one of the things possibly to mention here is that at Volume Graphics, we do have a consulting department. So we can be an independent advisor to customers that may be considering a CT system. There's obviously quite a few manufacturers out there. Most of them are partners of ours. We're good friends with them. But if a customer is interested in some sort of independent advice and consultation, then that's something we can do within Volume Graphics too.
How do you see the role of CT scanning in the industrial landscape changing or evolving over the next few years?
Well, I guess this is the really exciting part because, as I'd alluded to at the beginning, CT started off as mainly just failure analysis and has gone into metrology, but it's often kind of been about finding a better and more effective way to do analyses that have historically already been done. The beauty of CT is certainly looking into the future, and as I'd also mentioned earlier with additive manufacturing, it opens up a whole new world of options in terms of what we as I guess the human race can create. We can make so many more exciting things. So one of the huge things that I think will really be important for CT in the future is bridging the gap between reality and simulation. So simulation has become a lot more prevalent in terms of product development and making sure that you want to get your process as right as possible before you really start it. This makes sense. You can save money and time that way. And then you'll start making it and you have to start adjusting. And there's never really been a way to link those two. Whereas now, what Volume Graphics can do is we can take CT data, and one of the common things that you might simulate would be if you're casting things, where does porosity appear? Or you might simulate the strength of certain materials under certain loads. And one of the common materials that would be used for this is some sort of fiber reinforced plastic. And these two elements are now things that we can scan, and we can now scan and see where the fiber orientations are in fiber reinforced plastics. We can also see where porosities are within these samples that I mentioned. And we can now give this information back to simulation world. So they can use it either to validate their simulations, they can use it to improve their simulations. And obviously this is now slowly becoming a kind of closed loop. So we're helping take reality to improve the simulation world so that all the time we're reducing time to market and the costs involved in that. So one of the big things I think in the future will be closing this gap, which hasn't really been done yet. And also things like generative design. So this is also the hugely exciting thing, I think. Whenever I see anything that's done like that, they look so unfamiliar to us in terms of industrial components, and yet so familiar because they inevitably end up looking kind of biological. But because these shapes are so complex, they don't have your standard shapes, planes, cylinders, geometric faces anymore. And so they become so much more difficult to quantify once you've made it. And again, testing that would have been very difficult. If you try and use a CMM or a laser scanner to try and digitize certain areas, you wouldn't be able to see half of it. You wouldn't be able to describe these shapes properly. What a CT system does is it can completely digitize this model and get all of the information from these super complex shapes on the inside, on the outside, and then give you a method of volumetrically measuring it. So you could take the entire shape and just compare it directly to the CAD model that you started with, for instance. Or again, you can take this super complex shape and give that back to the simulation to see what would happen. So we're really going to help generative design take off, and I think that's genuinely super exciting just because I think that the parts look so cool. And then I guess finally, one of the buzzwords at the moment is this whole industry 4.0. So CT systems are going to become an integral part of smart factories. We already have customers that use CT systems at line, for instance, when they're doing plastic injection molding, just to keep an eye on their processes and all their injection molding machines running. You want to know, is the one that's right at the back of the room that's near the window, does that kind of change as the sun goes past? And all these slight influences you might have that can create variations in the quality of the components you're creating. If you have an inline CT system there as well, then obviously going forward with the smart factory, as the CT system can constantly measure what's coming out, give feedback that will then change the parameters of the injection molding machine, and all the time these measurements and statistics can all be recorded in a big database, and stuff like that, I think, will enable us to take a huge leap forward in general in terms of production. So they're the sort of things I'm looking forward to with CT in the future.
Oh, it's going to be fascinating to see some of that develop. Well, that's all the questions I had today. Thank you very much for your time, Ashley.
You're very welcome. Thanks for having me on.
You're welcome. Thank you.